sprinkle salt on ice, and the ice melts. You've seen it 100 times. On a sidewalk, in an ice cream maker, in a cooler packed for a picnic. Here's the paradox. Salt has never once melted a single piece of ice. Not one. In the entire history of the universe, salt has not made one ice crystal warmer. That should sound insane, because you've watched it happen. So here's the promise. By the end of this video, you'll know exactly what salt actually does instead. And it's a stranger, more precise mechanism than melting, one your textbook almost certainly got wrong. Salt doesn't attack the ice that's there, it arrests the ice that's trying to come back. This isn't a trivial wording nitpick, either. Salt melts ice, and salt blocks ice from reforming sound almost like the same sentence, but they describe two completely different physical processes, one where salt actively does work on the ice, and one where salt does almost nothing, except get in the way of something the ice was already doing to itself. Only one of those is true, and knowing which one changes how you'd explain everything from a snowy sidewalk to a science fair volcano. Here's the version most of us learned. Salt lowers the freezing point, so it melts ice. Full stop. That's the 1950s textbook version. Technically not false, but it skips the one detail that actually explains what you're watching. Salt does lower the freezing point. But lowering the freezing point doesn't mean generating heat or attacking a solid. It means something much narrower and much stranger. And once you see it, you won't describe salted ice as melting the same way again. To see why, you have to stop thinking of an ice cube as a frozen, finished object. It isn't. Even sitting perfectly still in your freezer at exactly 32 degrees Fahrenheit, an ice cube is one of the most frantic, busy things you will ever hold in your hand. Think of the surface of that ice cube as a small, insanely busy airport. On one runway, water molecules are constantly taking off, breaking free from the rigid, hexagonal ice crystal and joining a thin, disordered layer of liquid water sitting right on the surface. On the other runway, water molecules from that same liquid layer are constantly landing, wandering back, finding an open slot in the crystal, and locking back into place. At exactly the freezing point, takeoffs and landings happen at exactly the same rate. The ice cube looks perfectly still. It is not still at all. It's a dynamic equilibrium, a violent, constant, two-way traffic jam that happens to net out to zero. This isn't guesswork. The physicist Michael Faraday noticed something like this back in 1842. Press two blocks of ice together, even well below freezing, and they fuse into one solid block. If ice were truly a completely solid, inert object all the way to its surface, that shouldn't happen. Two solid rocks don't weld themselves together just by touch. Faraday proposed that ice must always carry an impossibly thin, liquid-like film on its surface, what modern physicists now call the quasi-liquid layer. The debate over exactly how thick that layer is and how it behaves has run for more than 160 years since Faraday first raised it, and it's still an active area of research today, studied with tools Faraday never had access to, from molecular simulations to atomic-scale surface probes. That's worth sitting with for a second. Nobody believed Faraday at first, because measuring a layer of water only a few molecules thick on a surface that looks perfectly solid to the naked eye was essentially impossible with 1840s equipment. It took well over a century for instruments to catch up to the claim. That's a useful reminder that "we can't measure it yet, and it isn't real" are two very different statements, one of the quieter, more honest lessons hiding inside this whole story. Now, finally, add the salt. Salt, sodium chloride, dissolves into that thin liquid layer on the ice's surface. The sodium and chlorine ions don't generate heat. They don't attack the crystal. They are, essentially, inert. Think of them as giant, dumb traffic cones dropped onto the airport tarmac. Here's the asymmetry that almost nobody explains properly. Those traffic cones don't sit on both runways evenly. The takeoff runway, melting, is driven by heat and by the ice crystal's own structure. Salt ions floating in the liquid layer don't meaningfully interfere with a water molecule's ability to break loose from the crystal. That process runs largely on temperature, same as before. But the landing runway, freezing, needs a water molecule to find a clean, open slot on the crystal surface and lock back in. Now half of those slots are occupied by an inert sodium or chloride ion sitting in the way. The water molecule bumps into a traffic cone instead of the runway and bounces off. So here's the honest, careful version, not the simplified one. Melting doesn't stay perfectly, mathematically unchanged, but it's the freezing side that takes the overwhelming hit. Takeoffs keep running close to normal. Landings collapse. And once landings fall behind takeoffs, the equilibrium breaks in exactly one direction. More molecules leave the crystal than return to it. The ice net melts, not because salt heated it, but because salt jammed the only mechanism that was ever putting it back together. Salt isn't a heater. It's a one-way traffic cop, standing at the landing gate with a barricade, waving every plane on the takeoff side straight through. This isn't just a metaphor, it's measurable, and the measurement has a name: freezing point depression. The formula is refreshingly simple. The drop in freezing temperature equals a constant, times how concentrated the dissolved salt is, times one more factor for how many particles that salt actually breaks into in water. That last factor matters more than people realize. Salt doesn't dissolve as one particle. It splits into a sodium ion and a chloride ion, roughly doubling its actual effect compared to a substance that stays in one piece. Plug in real numbers, and a roughly 10 Funtrum salt solution depresses the freezing point to around -6 degrees Celsius. Push it to 20 Funtrum, and you're down around -16 degrees Celsius. Keep going, and there's a hard floor. At about 23 Funtrum salt by weight, you hit the eutectic point, close to -21 degrees Celsius, the coldest temperature a simple saltwater mixture can reach, no matter how much more salt you add. Past that concentration, extra salt just sits there undissolved. It stops helping at all. That's why city trucks don't dump infinite salt on icy roads in a deep freeze. Past a certain outdoor temperature, more salt stops being able to do anything, because you've already hit the floor the chemistry allows. It's also why de-icing crews sometimes switch to other compounds, like calcium chloride or magnesium chloride, on the coldest nights. Those split into 3 ions instead of 2 when they dissolve, which pushes that floor down even further than plain table salt can manage. Same mechanism, just with more traffic cones per molecule dropped onto the runway. Once you actually understand the one-way traffic cop, 4 things you've probably wondered about separately turn out to be the exact same mechanism. That old-fashioned hand-crank ice cream maker, packed with ice and rock salt around the canister? Same mechanism. The salted ice around the canister sits well below 32 degrees Fahrenheit because its freezing point has been pushed down, letting it pull heat out of the cream faster than plain ice ever could. A cooler packed with ice and a little salt for a long day outside? Same trick. A salted ice water slurry can sit colder than 32 degrees Fahrenheit for hours, which is exactly why it keeps drinks colder longer than plain ice alone. City road crews spreading rock salt before a winter storm? Same mechanism. Industrial scale. They're not melting existing ice with heat. They're preventing the thin surface layer from ever fully refreezing into a solid sheet in the first place, which is why pre-treating roads before snowfall works better than salting after ice has already set. And the ocean, genuinely fascinating, because seawater is salty enough that it only freezes around -2 degrees Celsius, roughly 28 degrees Fahrenheit, not 32. That single number is why the Arctic Ocean stays liquid at temperatures that would freeze your bathtub solid, and it's the same freezing point depression math running at planetary scale. Even your own driveway is running a small-scale version of this every winter. When meteorologists warn that roads can stay icy even in above-freezing air temperatures, part of what's happening is the reverse of everything in this video. Without enough dissolved salt in the runoff, the landing lane reopens fully, and a thin, refrozen glaze can form again overnight, invisible until somebody's tires find it. The traffic cop only works while the cones are actually in place. I want to be precise about one thing, because it's exactly the kind of detail that gets flattened into a lie for the sake of a clean metaphor. It is not strictly true that melting is completely, perfectly unaffected while only freezing changes. Real molecular dynamic studies of salted ice show melting picks up somewhat too, just on a slower timescale than the sharp, immediate collapse in the freezing rate. The airport metaphor is a teaching simplification of something messier and more interesting underneath. What's solidly true, and what actually matters for everything in this video, is the direction and the dominant effect. Salt's main, overwhelming job is blocking the landing lane, not opening a new one on takeoff. That's the physics. The perfectly symmetric airport is a useful picture, not a perfectly literal one, and I'd rather tell you that than let a tidy metaphor quietly become a myth of its own. This is, honestly, the whole point of doing this channel the way we do it. It would be easy to hand you the clean, punchy version. Salt doesn't melt ice, it just blocks refreezing. Full stop, drop the mic, and never mention that real molecular simulations show a messier picture underneath. But the clean version and the messy, true version point in the same direction and support the same conclusion, so telling you about the mess doesn't undercut the big idea. It just means you now understand it one layer deeper than a headline could ever get you, and you know exactly where the simplification starts to strain. Next time you watch rock salt disappear into a slushy sidewalk, you're not watching heat. You're watching a one-way traffic jam resolve itself in real time, molecule by molecule. Which of the four, ice cream, coolers, road salt, or the ocean, surprised you the most? Tell me below. If your textbook gave you the simple version of something and left out the actual mechanism, that's exactly what the physics storyteller exists to fix. Subscribe to the Physics Storyteller. Next time on the Physics Storyteller, we go looking for another everyday, obvious fact that turns out to be quietly, precisely wrong. The ice on your sidewalk isn't losing a fight against salt. It's losing a fight against its own front door being blocked. Look at it differently tonight.